Welcome to Chapter 14 of our chemistry video series. Today we'll be exploring the fundamental concepts of acids and bases. Acids are often depicted in popular culture, like spy movies, for their ability to dissolve metal. Let's look at the science behind these substances. You might recognize the sharp, sour taste of citric and tartaric acids in candy. When these acids hit your tongue, they produce hydrogen ions that trigger a signal to your brain. While acids can dissolve many metals, the amount required to dissolve something substantial like prison bars would be far more than what you could carry in a pen. Here, we see aluminum dissolving in acid over time. To summarize, acids generally have a sour taste, can dissolve many metals, and are known for turning blue litmus paper red. Hydrochloric acid is a common laboratory chemical and a crucial component of our own stomach acid, aiding in digestion and protecting us from harmful bacteria. Sulfuric and nitric acids are widely used in industry and research. Sulfuric acid, in particular, is produced in massive quantities for use in fertilizers, batteries, and other vital products. Acetic acid, familiar to us as vinegar, is a carboxylic acid. This class of acids is defined by the presence of a specific grouping of atoms, known as the carboxylic acid group. Carboxylic acids are frequently found in nature. For instance, citric acid gives lemons their tang, while malic acid is found in apples and grapes. Bases share their own distinct set of properties. They taste bitter, have a slippery feel, and turn red litmus paper blue. Bases often feel slippery because they interact with oils on our skin. Many common household cleaners contain bases for this reason. Our sensitivity to the bitter taste of bases is likely an evolutionary adaptation to avoid toxic alkaloids found in some plants. Coffee, while overall acidic, uses these bitter basic compounds to create its distinct flavor. Common bases like sodium hydroxide are used in industrial processes and drain cleaners. Sodium bicarbonate, or baking soda, is a milder base often used as an antacid to soothe stomach discomfort. According to the Arrhenius definition, an acid is a substance that produces hydrogen ions when dissolved in an aqueous solution. For example, hydrogen chloride ionizes in water to form these ions. These hydrogen ions are highly reactive and quickly associate with water to form the hydronium ion. In practice, chemists use the terms hydrogen ion and hydronium ion interchangeably. When looking at a molecular formula for an acid, we often write the ionizable hydrogen first. This differentiates it from non-ionizable hydrogen atoms. Structural formulas help us see exactly how these atoms are bonded. The Arrhenius definition defines a base as a substance that produces hydroxide ions in an aqueous solution. Sodium hydroxide is a classic example, as it dissociates completely into its component ions in water. Under the Arrhenius definition, acids and bases naturally combine to form water. This process is known as neutralization. While useful, the Arrhenius definition has limitations, such as not applying to non-aqueous solvents. The Brønsted-Lowry definition expands our understanding by focusing on the transfer of protons in acid-base reactions. According to the Brønsted-Lowry definition, an acid is a proton donor, and a base is a proton acceptor. This concept was developed simultaneously by Johannes Brønsted and Thomas Lowry in 1923. This model clearly shows how acids like hydrochloric acid donate a proton to water, resulting in the formation of a hydronium ion. The Brønsted-Lowry definition also explains how substances like ammonia, which don't contain hydroxide ions, still act as bases by accepting protons from water. Crucially, in the Brønsted-Lowry framework, acids and bases always work in tandem. Every proton donation requires an acceptor. Some substances, like water, are amphoteric, meaning they can act as either an acid or a base. When we reverse these reactions, we identify conjugate acid-base pairs. A conjugate acid-base pair consists of two substances related by the transfer of a single proton. To identify these pairs, remember that a base accepts a proton to become a conjugate acid, while an acid donates a proton to become a conjugate base. Neutralization reactions occur when an acid and a base combine, with hydrogen and hydroxide ions forming water. A salt is also produced as a byproduct. When carbonates or bicarbonates react with acids, we see a gas evolution reaction, which releases carbon dioxide in addition to water and a salt. Acids can also react with many metals to produce hydrogen gas and a dissolved salt. This is essentially how metals are brought into a solution. However, not all metals react with acid. Gold, for example, is resistant to such reactions, which explains why acid-filled pens won't dissolve every metal object. Acids also react with metal oxides, resulting in the production of water and a dissolved salt. For instance, hydrochloric acid reacts with potassium oxide, and hydrobromic acid reacts with magnesium oxide, both following this pattern. Moving to base reactions, the most significant is the neutralization of an acid. We also see unique reactions, such as sodium hydroxide reacting with aluminum and water. Interestingly, aluminum dissolves in bases, which is why aluminum piping is typically forbidden in plumbing codes. We can quantify the amount of acid or base in a solution through a laboratory procedure known as titration. In a titration, a substance of known concentration is used to react with a solution of unknown concentration. Here we visualize an acid-base titration. We focus on the reaction between hydrogen ions from an HCl solution and hydroxide ions from a sodium hydroxide solution. Spectator ions, like chloride and sodium, are omitted for clarity. During the titration, we add the known solutions slowly to the unknown. At the equivalence point, both reactants are fully consumed according to their stoichiometry, meaning neither is in excess. The equivalence point is reached when the moles of added hydroxide equal the moles of hydrogen originally present. We typically signal this point using an indicator, a dye that changes color based on the acidity of the mixture. In this specific titration, phenolphthalein serves as our indicator. It is colorless in acidic solutions and turns pink at the equivalence point, providing a clear visual signal that the titration is complete. Let's walk through an example. We need to find the concentration of an HCl solution, given that 10 milliliters of it requires 12.54 milliliters of 0.100 molar sodium hydroxide to reach the equivalence point. Our strategy involves writing the balanced equation and using a two-part solution map. First, we determine the moles of HCl reacting with the known amount of sodium hydroxide. Then we use that quantity to calculate the unknown molarity. By performing the calculation, we find that the HCl solution has a concentration of 0.125 molar. Checking our units and logic confirms that this answer makes physical sense given the one-to-one stoichiometry. It is important to distinguish between strong and weak acids. A strong acid, like hydrochloric acid, ionizes completely in solution, whereas a weak acid, like hydrofluoric acid, does not. When strong acids dissolve in water, the entire substance converts into ions. For HCl, this means the solution contains hydronium and chloride ions, with virtually no remaining intact HCl molecules. Pure water is a poor conductor of electricity due to a lack of ions. This is why contaminated water is dangerous near electrical devices, as those dissolved ions allow electricity to flow through the water and potentially your body. In contrast to pure water, a strong electrolyte solution like hydrochloric acid conducts electricity well because of its abundant ions. This flow of charge completes the circuit and powers the light bulb. To wrap up, there are 6 primary strong acids. We categorize them as either monoprotic, which contain one ionizable proton, or polyprotic, like sulfuric acid, which can provide multiple protons per molecule.